Okay, SBC details. So a few things we want to talk about here. Performance, how to optimize the performance of the system and what affects the performance. We have, I have some details on installation. Installation is pretty well described on the wiki. Here I just give a few additional notions to make sure it is understood. Then I talk about the SBC internal architecture, so that allows you to understand better how it works, and if you need to troubleshoot something, you will understand how it works. I will talk about the type of protections you get on the SBC and how they work. Access control list that you have on the systems, and SBC status, how to get the SBC status. Okay. So there are really two factors in the system we have to verify and that can affect the performance. One is the call rate you get in the system, so how many calls per second you will get. The other one is the number of sessions, maximum number of sessions you can process in the system. So depending on the platform type, you will get more or less performance. Okay? So in general, a bare metal server will give you the best performance for a certain type of hardware architecture. If you run a virtual system on the same architecture, you will get in general, you know, maybe 10% performance loss, or 15% or 20%. So you will have some loss of performance if you go virtual, but of course you have all the advantages of being on a virtual system. And then on the cloud architecture, we cannot reach more than 5,000 sessions. The main reason we cannot reach more than 5,000 sessions is that the interfaces that are provided to the SBC in the cloud architecture are limited in bandwidth and packets per second. And since we run a service which is not bandwidth intensive, but packet per second intensive, then we reach the limits of those cloud interfaces that are provided to the system. So if you and the other thing is, on the cloud, you need to have a bigger implementation if you want to pass the RTP in the system, or bigger instances, I should say. Unless you do just the SIP traffic and you don't pass the media. Okay? If you pass the media, then you can go higher than 5,000 sessions. All right, so the CPU specifications you can use for running your system. There's two factors that you can that you need to be interested about. One is the number of cores and the core speed. All right, so number of cores you have on the system, because you need a minimum number of cores to run the SBC. Some of these cores are reserved for the protection mechanism, and some of these cores are used for the rest of the call processing. All right, so you need to have a certain number of cores depending on the target system you want to achieve. And the core speed, each of these cores will have a certain performance, and it will tell you how many calls per second you can do if you have more CPU speed there. Okay. Let me show you here. When you configure the system initially, you are asked if you want to dedicate some cores to the interfaces. So you should always dedicate the cores unless you plan to use less than 500 sessions on those systems. Okay, so if you plan to do more than 500 sessions, you should always dedicate the cores. You will have also a reserved CPU for processing the network interfaces. All right. So for, let's say, around up to 1 gigabit per second interface, you will need to reserve at least 1 core. And for each 10 gigabit per second interface, you need to reserve 2 cores to process the traffic. The reason we want to reserve some cores is that to be able to protect the system, you need to be running at line rate. To be running at line rate, you need to process every single packet that comes in the system and decide what you want to do with it. Do you want to drop this packet? Do you want to keep this packet in the system? All right. So the only way to do this is to make sure that all packets are received, and to make sure the core is not interrupted by other services in the system. We need to reserve it for that specific application. All right. So that's why when you look at the CentOS service and you see that the application is using 100%, then it's using 100% because it is reserving the core for processing the packets, even if it's not running 100% all the time. All right, so we have other status we can see that tells you exactly the real CPU usage that is used by the system. All right, so this is in the web portal. You can see this, and but if you use just the tool like top on CentOS, you will see it's 100%. And if you have 2 cores, then you will see 200% used, completely used by some applications. Okay. So you need to have enough cores to support the network interfaces that will be facing the network. These information are defined in a file that is used for the configuration of the system. And that file is called nic.json. Okay, so this file is created automatically when you configure the system initially. But if you think that you can have better performance, or you don't reach the performance you are requiring, it is possible to change this file to optimize the configuration. Okay. We have actually done it last week for one of our customers, which is also doing some call center application, and he was limited to around 300 calls per second. When we looked at this file, we saw that there was too many cores reserved for network interfaces and not enough for processing call rate. So we improved the system by changing this file and restarting the system. For changing this file, well, you will need our help to do this, right? Because it's a very cryptic information. Okay. So here is an example of a system. You have your all your CPU cores running here on the system. In this case, there are 6 CPU cores and 6 hyperthreads running on that system. All right. It runs, so usually when you look at the specifications of the processor, it's going to tell you 6 core, 12 threads. All right, so this is a 6 cores, 12 thread system. Now, for being able to receive traffic from network interfaces, TB router will need to reserve a CPU core. When it reserves a CPU core, it will also lock up the hyperthread. All right? So it's actually 1 CPU core and 1 virtual CPU core that it locks up when you allocate, when you dedicate a CPU core to the system. All right? The reason that we do this is so that TB router doesn't get interrupted by the thread for being able to process all the packets and make sure we don't drop any packets. So we can reserve one core like this for up to 5 1 gigabit per second interfaces. Each 1 gigabit per second interface can have 5,000 sessions, but not SIP sessions, but RTP sessions. All right, so you can have 5,000 calls going through the SBC per network card if you are using G711. If you are using G729, you can have more sessions than that, at least a double. Because G729 takes half the bandwidth of G711. Then you have, if you have a system like this, you have 5 interfaces dedicated to one core. You have like a lot of other threads here that can be used for the rest of the applications. I already showed you the gateway application, the engine application, and maybe also SIP. And each one of those will run and will take the bigger part of one thread of the system. All right? And these are the 3 most critical applications, and they will qualify the number of calls per second you can do in the system. The other applications are used for like the web service, SNMP, and stuff like that. And so usually they don't use a lot of processor, and all of the other applications can run just on one thread. So if you look at a system like this, you need to have 3 cores and 3 hyperthreads to run this system. Okay, so normally you can't get a system like this, but maybe a system with 4 cores and 4 hyperthread is enough to run a system and to have maximum performance. Okay. The other ones will not be used so much for the SBC here. Okay. Now, I say this because one CPU core here running at high speed will give you more performance than one CPU core going at a lower speed. And usually when you want to choose a server, you can have servers with a low number of cores and high CPU speed, or a lot of cores with a low CPU speed. Right? So having a lot of CPU cores will allow you to have more network interfaces, but less calls per second. Right? Because the CPU speed on larger systems which have more cores have lower speed. Okay, the question from Rudy, is it possible to have multiple gateway application in one SBC platform, or set multi-core for app gateway? So right now we cannot. Okay, we cannot do that. So gateway will run only on one CPU, on one thread. The engine also will run only on one thread, and TB-SIP as well. So of course we have plans to improve this, because gateway can be doing a lot of things. If you're doing routing scripts and the routing scripts are complex, the load will all be on this application. The others will be not so busy, and then your system will be limited by this one. However, right now, we can only run it in one thread. We have plans to improve this. I'm thinking that this summer or beginning of Q3, Q4, I mean, we should have something that will be improving the performance of this particular application. Okay. If you have a 10 gigabit per second interface like this one here, you need to have 2 cores dedicated to capturing the traffic here. And you also need to use those hyperthreads, right? So it's going to use 4 virtual CPU to be able to process all the bandwidth that is received here. And yeah, but 10 gigabit per second can give you 50,000 session if you're using G711. right? So you don't need a lot of those interfaces to cover large systems. If you have two 10 gigabit interface, then you need to have 2 more cores for that. But you see here, even when you have a 10 gigabit per second interface, you still only need 4 cores to run all the system. All right, so a 4-core system usually is enough for for having the maximum performance, and the CPU speed will tell you how many, what is the call rate you can do on the system. Questions on this? Or other questions, I should say. Okay. Let me come back to this right after. I should have put it after these slides, okay? So the bare metal installation. So you have a server that you can install the software. You will load the ISO image that we provide. This ISO image includes the SBC application plus the CentOS kernel. So it has all the software included there. This ISO image is not, let's say, it's not necessarily to the last version. Okay, so maybe you can have an ISO image running version 3.1.10, and then you can upgrade the system to the version that you need to be running. So maybe after you install the ISO image, you still need to upgrade the system to use the version that you want. Every now and then, we will update this ISO image and make it available to you, so that you can install new servers. Then there's a CPU running here in the SBC, which has the number of cores and the speed of each of these CPU cores. And this will tell you what is the performance you can achieve with this system. You always have a management interface to connect to this SBC. This one is not protected by the SBC, so it goes directly into the CentOS kernel. And it allows you to configure all the system, including the SBC functions. Then in normal cases, you have a WAN interface and a LAN interface connected on the SBC for going from the outside network to the inside. But you can have more WAN interfaces, more LAN interfaces on these systems to interconnect various networks. We have tested some servers that are available on the market, and we have specified these server on our TB Okay, so you can search for certified hardware to find the TB wiki link. And these servers, well, we've tested some of them up to 60,000 session, 30,000 session. And then other devices for, these are more CPE type services, but a Quotum box here, I think it goes for like $500 or something like that. And you can do 5,000 sessions. And also here, I tested the LANer device, just a bit more expensive, but maybe has more features for reliability in here. And I'm testing now, or maybe next week, I'll be testing another LANer device, which is a smaller version and which is also cheaper. So you can see and compare a server that you want to use to make, to have an idea what will be the performance of your system. Okay. When you do a virtual installation, Then you have also your hypervisor that will be running here. You will have a virtual image that you will load inside the hypervisor's disk space. And then usually you have some kind of profile to start an instance. And that profile will say, I will assign a number of CPU, I will assign memory, disk space for the SBC to run. And these criteria of instance that you start will definitely be giving you the performance of the system you can achieve. Okay. Then, like we were explaining yesterday, we have network interfaces that are physical interface connecting to the physical device that runs the VM system. And here you will have some network interfaces presented to the SBC. These interfaces, depending on which type of VM, it could be E1000, VMX-Net3, MAC VTAP, SR IOV, and pass-through. Okay? So these ones are all emulated interfaces. These are a bit more efficient interfaces, these two here. And if you want to reach, and these are limited, most of them are limited to about 5,000 sessions or maybe just a bit more than 5,000 sessions. If you want to reach more than 5,000 sessions on a virtual machine, you will need to use one of those two methods here, which is SRIOV or pass-through. And what does pass-through do is it go around the hypervisor and connects directly to the network device here. So it bypasses the network copying, right? The packet copying that goes on in the hypervisor, and we can reach directly these physical interfaces. Same thing here, you can have a pass-through interface like this. So with a pass-through interface on VMware, we tested, I think it's up to 26,000 sessions. All right, so that's the only way to reach higher capacity is with pass-through. SRIOV is almost the same as pass-through, except that these network interfaces can be shared amongst multiple the other applications here. So they can be shared here. So you can have SRIOV connecting here and SRIOV connecting here on the same network device, but with a very good performance. Okay. So both of them are very similar here. But not all the systems support SRIOV. So you also have a management interface that you can reach the system here. Which is independent from the TB router or SBC functionality. But usually you also have the console here that allows you to connect to the system, which is very useful when you try to want to access the system and you lost maybe other type of access to the system. Platforms supported are VMware, KVM, OpenStack today. So these are the ones we support. Yes, James. Yeah, but you get it in China, right? So maybe for you it's cheaper, the Kotam box. So I think we got it for $400 here in Canada, but from China, yeah, $200. Good chance you do that. It's the device that we presented here. Whoops, that we presented here. This one is it's a 4-core Atom processor at I don't know 1.3 or 1.5 gigahertz, something like that, and it's surprisingly very efficient. Right, so it can crunch a lot of traffic through that without budging. Right, so yeah, I agree with you. Good units. So a cloud installation is a little bit different. So you will have a region The region here has to be, when you start your instance, it's going to be in that region. The reason why we want to use a region is so physically these devices are in one place, and when you want to send traffic to another region in the world where there is some delay when doing that, so you want to be as close as possible to your destination so that you don't induce delay going through network devices through the national interconnection or international connections. Okay, so you need to be in a region, and in those regions you have cloud subnets, right? So various subnets that you can use here. Why we want to use things in the same subnet is when you have other applications that you want to interconnect with your SBC. You want to be in the same network here because this traffic here that you pass inside the subnet will not be charged, right? Because it's just running locally on the system. On cloud networks, you will be charged for traffic going out on the WAN network here, right? So you have to be careful. Every traffic that you pass here will be chargeable. Then you have your cloud storage, okay, that is residing somewhere, and we will share you an image, or you will load it here in the cloud storage, and you will then start your instance, and you need to choose your instance type here. The instance type is how many CPUs you have, what is the memory that is assigned, type of disks. And in our wiki, we propose some number of CPUs and memory for certain type of performance you want to achieve. Okay. Here, when you start your instance in the cloud, you will have always a private IP here, and it will be always DHCP, right? So it needs to be an address that is given by the service here. So when you start this, it's going to provide you an IP here. And you will also be getting a public IP that you can reach the system. And that's what I was explaining yesterday. You see, there's always an adder here to convert from the public to the private network here. All right. So the basic configuration is to have only one interface for both management and public network. However, you can add other more network interfaces on your device, and then you can run traffic on both of these interfaces. We support right now two platforms, AWS and Azure. AWS is Amazon, and Azure is Microsoft. And the question is it possible that cloud-based SBC support hardware transcoding? It could be possible. However, you will need to have interfaces here to the physical transcoding device, which would be outside, because now we offer just a hardware device for transcoding. So I would say if you really want to do transcoding, the cloud-based solution is not the best one, because you would need to add an interface to control the system and another interface to pass the RTP traffic. This will generate a lot of traffic through the public network, and it's like, oof, it's yeah. I think for now we should not do this. Okay. In our roadmap, we do plan to have a software transcoding available that you could connect to the SBC, but for some reason, it's always there's always stuff that have more priority that comes in, so it's being pushed in the roadmap. All right. Yes. Okay. So there was a question on real cores versus real core versus vCPU. Okay, a virtual CPU. So a virtual CPU in a cloud infrastructure is they give you a thread, right? This thread could be running as a hyperthread or CPU core. You don't really know where it's going to run, and it could be shared with other services, right? So a virtual CPU, you don't know if it's a real core or if it's a hyperthread or so. I hope it answers that question. Then we have high availability features on the system. So 1+1 support. Okay, so if you have 1+1 support, then this is available on all the platforms, but not the cloud platforms. These are the two cloud platforms here, and it's not supported. Active is just to have two different SBC running as active, and it's supported on all the platforms. And then Ethernet bonding, well, we added just recently to have Ethernet bonding when you use bare metal. So if you need to use that, please tell us, and we can give you the version that will do this. Then you have Ethernet bonding. It says not available because we usually do it on the hypervisor itself. So the hypervisor will manage if you need to do Ethernet bonding there. We don't manage it at the SBC level. All right, now if we look at the internal architecture of the SBC, you have on your system, so this system here can be it can be a bare metal or any other system here. Okay, so we only look at the SBC portion of the system. You have in there, let's say, three main modules. One is the CentOS operating system that is running on the server. Then you have all the other SBC applications except TB router. So you have here the gateway application, the engine application, TB SIP, the web services, SNMP, call tracing, everything is running here, but not TB router. TB router is running as a separate entity here. And I show it here because it has direct access to these interfaces. And the traffic that comes in to the system, any WAN or LAN interface, will need to go through TB router before it goes to the SBC applications. We will set a list of rules that will be accepted by TB router, and these rules will include SIP messages and maybe other web services and stuff like that that will be able to pass through the Linux kernel and then to the SBC applications. You also have rules for RTP and SRTP that are created. So when there's a SIP call that is made and RTP is allocated, we will open here some ports so that calls can come in and be relayed to the destination. All right. So these ports will be available here. You see here the management part is running separately, and this one has direct access to the CentOS kernel and also the SBC applications. So it passes separately. It doesn't go through TB router, so it doesn't go through the access control list, the firewall, or anything. All right. So this interface that you use here, you have to be careful that it is not on a public network, so people can have access to this. Okay. For SBC with no transcoder, is it become bypass RTP? Okay, so let me come back to your question in just 1 minute. The reason we do it this way is to have maximum performance on passing these packets and maximum performance on making sure that all the traffic that comes in here is being processed correctly, is being dropped if it's not valid traffic, or is being accepted if it's valid traffic, and accepted and sent either to the kernel and SBC application or as RTP traffic to the other system here. And this also shows you why you cannot do a TCP dump here to capture the RTP traffic. Okay, so if you do a TCP dump here, well, you will see the SIP traffic because it passes through here. You will see, you know, web traffic if you have a management interface here and other traffic here. You will also see the management traffic because the TCP dump can capture everything here, but you will not see the RTP and SRTP. You need to use TB router to be able to capture this type of traffic. Okay. So it's normal that if you use TCP dump, you will not see RTP and SRTP. So, and this part here is of course optimized to carry the RTP and SRTP traffic. And when you do network transformation like this, then there's copies that are done in software and it's not as efficient. So when you are using transcoding, you connect your device to the bare metal or the virtual machine. Okay? And when you do this, you need to have 2 additional LAN 1 interface. Okay? And usually we name them trans, T-R-A-N-S, transcoding, trans 0 and trans 1 to be able to connect to this transcoding unit. They are still LAN 1 interfaces because they need to be controlled by TB router here. When you receive traffic here and it needs to be transcoded, the TB router will say, okay, I will reserve a resource here on this device. We will send a certain type of traffic on the transcoding device, and then it's going to be sent back out to the other network. All right. This one here, you see, can be just a private network. So you can just keep all of this in a local network. So here, for example, you have G711, and on the other side, you will have G729 being sent to the destination. Okay, so this is a typical use case for this. If the system knows that you don't need to transcode, so even if there's a transcoding device, if it knows you don't need to transcode, well, it's going to just bypass and go directly to the destination like this. It will not use this internal interface. Okay, so if there is a SBC without transcoding, does it bypass the RTP? The answer is no. Okay, so if there is transcoding or if there's no transcoding, it will always pass the traffic through TB router or through the transcoding device like this, unless you configure it differently. And you have to say, I want to force media bypass on this network access point. All right, so let me show you where that is. In the profiles here, you take any one of those profiles in from the system. Media relay, you will say use RTP no anchoring. All right, so use RTP no anchoring. The description is here. This is a variant where RTP is not going through this SBC unit. All right, so you need to set that. If you set this here, then any network access point that use this will bypass the RTP. It will not go through the SBC. Rudy, does that answer your question? Okay. Now I thought I had mentioned this here, but I don't see it. So if you do SRTP to SRTP, it's gonna go directly like this from TB router, and there will be no conversion necessary. If you do RTP to SRTP, it's still gonna go through like this, but TB router will do the conversion from RTP to SRTP, and this requires some CPU usage from the system, okay, to do this transformation. So if you need to do a lot of RTP to SRTP, you may need more cores assigned to TB router to be able to process all this RTP to SRTP traffic. Okay. So I'm talking about thousands of sessions, not hundreds of sessions, right? So you can monitor here the CPU usage of TB router when you're doing a lot of RTP to SRTP, and you can see what is how much CPU is used on that TB router. And let me just show you that quickly because it can be interesting to see it. Let me connect to this one. Oops. So again, you can see it from the web portal, but you can see it from this TBX CLI tools. And let's say I will choose here TB router. You will see here the real CPU usage used by the cores. So some of them you see are unused, some of them are 3%, and you can see all the details, how many packets per second it's processing, megabit per second, and stuff like that. So you can see it here. Or you can see it from the web interface. In the, well, actually I'm at the right place here, host, status, and then you have processor usage. And you can see here the packet processing being used currently. Okay, so that's when you're doing RTP traffic and or RTP to SRTP, this will go up. And you see here I have 100% available for each of these interfaces. Okay, so that's, I can know here that's one CPU core available for this interface. Okay. So internally in the system, we run a lot of applications. We have talked about many of them already, like TB router. We talked about gateway, which has the routing scripts inside. TB SIP, which does the SIP stack analysis. And then we have engine, which does a few things, like it manages the stream server and also some configuration of devices here, but yeah, okay. So these ones we saw already. The web portal is the interface where we configure the system. And when you connect through the management part, through the web portal, and you make some changes, they are pushed in the configuration database here. And when you do a database backup, a backup of the system, it's going to do a database backup. And then all your configuration is stored here. When you are ready to activate the configuration, what happens is that you tell all the other applications, go and read this new configuration. Okay, so this one will read the configuration, this one will read the configuration, and it will update all the applications so that they know what is the new target configuration you want to achieve. All of this is done live in the system. Okay, so you can activate this configuration at any time. Yeah, so let me just show you some examples here. For SIP traffic, the SIP traffic will go through these interfaces, or the LAN 1 interfaces, which are here, through TB router. If it is accepted, it will be sent to our TB SIP application, then to engine, and then to gateway. You see here, there's two lines going to call trace. So both of these applications will write information in the call trace. And that's what you see in the call trace when you look. You know, you will see the messages that came in, that goes out, but you also see stuff like playing, recording, and these things will be done by another application that's called engine here. If you have RTP and SRTP traffic, well, it can go just directly to TB router here. So you see no other applications are affected by RTP and SRTP traffic. Or if you have transcoding, then TB router will also send it to the voice over IP hardware for transcoding and send back out. Again, other applications are not affected by the traffic. This is why we can reach 20, 30,000 and 60,000 sessions. Okay. The other applications we have here is SNMP, which we'll show you later. There's some logging on the system. This application here is upgrading all the system, making sure they're all running at the same version. Stream server here is for playing and recording. Right, so you have these other applications that are running at the same time. So correct. The question is, in call trace, we can only see SIP signaling and no media. Correct. So what you see in the call trace here is only the SIP signaling that is sent here. And you don't see the RTP traffic because it's running here. Right? However, you get some statistics on the RTP traffic, because when the communication is finished, there will be data relayed in those systems here, and it will say, well, in that communication, maybe I lost 3 RTP packets, and engine will know about this and push this trace in the call trace. And you will see at the end of the call, what is the mass of this call, how many how many packets were lost, and a lot of other statistics. Okay, so you don't see the RTP traffic, but you will see like the report of the quality of this particular call. Okay, so the question is there any way to store all the call trace passively, like Voight Monitor or Homer? Okay, so here what we do is we get data from calls that are ongoing in the system. These call traces are in memory, so you can access them directly from the web portal and see the last, it's configurable. So by default, it's 10,000, but you can go to 50,000 or 100,000 last calls will be displayed in the call trace. We also store it on the file system. So the call trace will store on the file system the call trace information, which is compressed so that it doesn't take a lot of space on the system. Okay. This can be viewed later. Okay, so you can view the old call traces. Okay. Now, we VoIP monitor. VoIP monitor, what it does, it can monitor the SIP traffic and the RTP traffic, and it can give you statistics on call information or statistics on the calls that went through the system. And I know VoIP Monitor is a very nice tool. I have heard of Omer. I didn't see Omer, but I know it's also a good tool. However, these tools are not optimized for doing thousands of sessions in the same system. Okay, so we did try VoIP Monitor at some point, and it just gets overloaded if you go more than like 500 sessions or something like that. So it's a nice tool, but it's not adapted to the SBC system. And when you want to do 20,000 sessions or something like that, these tools just won't work. So we have other ways of getting the data you need. But it would be nice to have a tool like VoIP Monitor that would work on this for sure. Okay. So here it's just the description of each of these applications. So we talked about them already, and you can refer to this later if you need. Okay. So for example, when I talk in the presentation of engine, and if you look really physically on the CentOS system or on the toolpack on the web portal, you will see toolpack engine. Okay. So that's the real name of the application. And call trace, for example, is called TBUCT writer. So UCT is unique call trace, and writer means that it writes into a file. Okay, so you have these applications and other applications like that. Like I said, stream server is for playing and recording media files, and SNMP, the application is called TB SNMP agent. So just for your reference. Okay, and then you have some applications that run active-active. Some are active standby and some are master slave. So TB router runs active-active, OAM also. So that means it runs on the both systems at the same time. Syslog, so you get logs from the system on both 1+1 systems. SNMP runs on both, so that means you can access SNMP on both systems at the same time. And the stream server application runs on the two systems as well. Okay, so any one of them, if one of them is up, this will work. You have other applications that work in active standby mode. So for example, gateway application, the application that's running the routing scripts will run only on one server, and it will be on standby on the other server. So then all the processing is done on one of these gateway applications. And if ever it fails, then the gateway application on the secondary system will take over and resynchronize the active calls that are there and continue processing. All right. Engine is the same. It will also resynchronize active calls in the system. System manager is the same. The one that is running active standby but does not resync the calls is SIP or TB SIP, and so if TB-SIP crashes on one system and it starts on the other, you will have lost all the calls. So we do have a project to do also a synchronization like we do for gateway and engine. We have a plan to do it for SIP, but right now we don't support this. Then you have master slave. So TB router also runs as master slave. Okay, so it runs on the two systems at the same time, but one of them will have priority. Right? And OAM is the same. Both of them are running at the same time, but one of them has priority. Right? The database is the same. It runs as master slave. So one replicates from the other, and it's chosen by the system which one is master, which one is the redundant database. So the question, example on 1+1 system. If gateway application failed on host 1, then gateway application on host 2 will take place. Correct. All right, so you have gateway running on, let me show you the next page here. You have gateway running here. You see gateway application is running as active on server VM-A3. And then you have another gateway application running as standby in VM-A2. So you can see this application status list in the web interface. Okay, so if gateway fails here, for example, then this one will then become active. Okay, so the question is, I was thinking that host 2 will take place completely, including all applications and TB router. So this is, let's say, not true right now, but this may be changed when we do the TB-SIP redundancy. Maybe everything will switch together. Okay, but right now, the way it works is if you kill gateway application, because you can do your tests, right, and go in and kill the gateway application to see if it's going to switch over. If you shut it down, the gateway will run on the other system, but all the others will remain the same. So they will not be switchover of all the applications when you do that. Okay. And you see here active standby, active standby, active standby. Whoops. No, not this one. Active standby here. Toolpack engine, active standby. Okay, so you will see them. You will see them, the status here. Okay. For testing also from the web portal, you can change the target state here. You can say stop, and this will also switch over. Instead of doing a kill application from the CentOS kernel, you can do here just a stop. So maybe I can just show you this. So here you have host applications. And then if you click on, well, I want to have a 1+1 system. Wait a second. Yeah, okay, so this is my 1+1 system. Okay, so if you do applications, click on applications here. So you see all the applications that are running on the system, and you do status. Then you can see where it is running as active. Okay. Then if you want to, let's say switch over. So I'm running this one as active, and I want it to run on the other system. So I can go here from the web interface and then set to don't run. Okay, so here I'm gonna force stopping the application so that there's a switchover. Okay, and if I do refresh here, you see OMN current state, it says not running. So now it stopped. All right, so if I go back to the application list, you see that my gateway application here, it says target state don't run, and it's not running. And then it's running on the other system now as active. So it just switched over. All the others stayed the same, right? So see, TBOM app here is still running on A2 as active, and probably engine also. I don't know where it's running now. Well, engine is running on A3, but it's just a chance, right? But you know, this is only for testing, because normally you should leave them always running at the same time. Okay, so now it's running, and if I look back here, so now it's still in standby, right? We won't switch over again the application if it fails. If it, I mean, if the other one comes back, okay. And you can see this yesterday. I think I showed you this already. If you use this tool, you can see colors here, and you can see which one is the primary server, which one is the secondary server, and then the applications that are running active, standby. So you can have a quick look of what is the state of your system. And so you can see this here. Blue is master slave here. TBA router, unfortunately, has no colors. So you don't see which one is active and which is slave, but the other ones do. Yeah, we talked about this a little bit. I just want to revise this. You need two control ports in one person redundancy. You will have a MySQL database replication. So we're using a MySQL database or MariaDB, and we use the replication scheme from those databases. This works great on the systems. The replication is very efficient. So you have all the application that runs here and all the application that runs here. Some of them are standby, some of them are active or master. All of that is managed automatically by the system. So you don't need to do anything else. And unfortunately, it's not supported on the AWS and Azure platforms right now. And the logs and CDRs are stored separately on each servers. So these applications have logs that are generated, and they will be stored locally on the system here. And these applications will store the data locally here. So if you have a failover on a system, well, you need to get the logs from this system and this system to get all the information available. This is one of the reasons why when I was talking about call detail records yesterday, if you use call detail records and you want to push them out to another server, you need to do or to have this active on both systems, because if it fails over here, the CDRs will start being generated here and you will need to send them from both systems. Okay. So here we have denial of service attacks. So the goal of DOS attack is to use all the resources of a system. And then this will block access from other users to access the system. And usually a DOS attack is only from a single IP address. And it sends a lot of traffic that is either valid or invalid. Sometimes invalid traffic is more damaging than valid traffic. And the thing here is it may come from a known device. So maybe you have allowed this IP in your system, but you're getting flooded with traffic from that particular source IP. Okay. So the goal of the SBC here is to identify the behavior of this attack and shut down the traffic coming from this source. All right. So When we say shut down traffic from the source, it's shut down all the invalid traffic. All the valid traffic that would have been accepted already will continue to flow. Okay. Then you have distributed denial of service attacks. So these are attacks coming from a lot of different source IP addresses. Again, it may try to send valid or invalid requests, and it can also be valid IP addresses, right? So so we need to make sure here that we process all the traffic that's coming in, and we make sure we drop all this traffic. Okay, so how do we protect against these types of attack is we need to support the full rate of incoming traffic. So let's say you have 2 times 1 gigabit per second of traffic. We need to be able to process each individual packet that comes in these network interfaces and decide for each one of them if it's good, trusted source. If it's bad, drop it. Right? And then we need to monitor the traffic from trusted sources to make sure it doesn't go over the limit of over certain specified limits, which I will show you. So if the traffic rate is too high, for example, we will ban the traffic coming from those sources. And the default is to ban for 5 minutes. But I will show you, and there's different values for different modules, different type of traffic, okay, or protocols. So DDoS is just a bit more complicated to manage because you may not know when it's a DDoS. Okay, so the only way to figure out this is a DDoS attack is that every time we get a packet that is an invalid packet, we will add a drop entry and make sure that this packet is dropped immediately in the system. And if we get a lot of those drop entries in the system and it is full meaning that we have reached the maximum that we have configured in the system, then we'll stop getting the traffic from these sources. Okay. The second thing that can happen is that the processor usage is too busy. But in our systems, the way we design them and configure them, if you're using the dedicated mode of network interfaces, you will never reach the processor usage maximum. Okay? So we just need to make sure it's configured correctly, and this will not happen. So if ever we reach this drop entry full list, and we decide to move to a DDoS mode, well, there will be a status in the system to show we are in DDoS mode. There will be, if you have SNMP, you will have a trap that will tell you there's a DDoS attack in the system. And yeah, you see it in the status, and you see it in the as a SNMP trap or SNMP get. Okay. If you get it the DDoS, you will block all this traffic except the ones that were already opened. Okay, so the ones that were already open, we will keep them running. So the SIP calls that were already active, the RTP traffic that was already flowing, we will keep it flowing into the system, but we will block all other new calls being made in the system because we have reached our drop entry list. There are other services that will not be blocked as well. By default, the SSH connection is not blocked, SNMP is not blocked, but you can change this if you want. So how do you decide that? Is you have a special rule in the system that's called DDoS protection. Oops. That's called DDoS protection. And if a rule is before the DDoS protection, then it will be accepted. If the rule is below DDoS protection, it will be blocked. So let me just show you this quickly. Oops, not this one. I want to show is this one. Okay, so you have here rules that are created in the system. These rules are created automatically when you configure the system. So when you configure SNMP, it will add one entry here for SNMP. If you have a SSH, which is normally the case, you will have it here and HTTP here. And then you have the special rule that's called DDoS protection. And then you have other entries below. All right. The rule order is like a firewall. So it goes through the first one. And the first one, if it's accepted somewhere, it will come in. If it's dropped, then, or if it doesn't reach any one of those rules, it will be dropped. All right. So let me just go back here. There are also other special packet types. ICMP, ARP, and DHCP, and there's an automatic limit on these types of packets. 100 for ICMP and DHCP, and they will be dropped if we reach these levels. ICMP can be disabled in the virtual port. Okay, so for each virtual port, you can say, well, I don't want at all to respond to ICMPs. ICMPs are pings, right? Ping requests. So you can say, I don't want to have ICMP requests. Any broadcast and multicast packet is multicast traffic, I mean, is dropped automatically. RTP is created automatically by the system. So it does not show in the rules, but it will be handled automatically. Okay. The RTP, there's another special thing about the RTP is that at the end of the call, the firewall port for RTP will remain open for a little while, so that any RTP traffic that has not finished from the remote side will not be replied with a destination unreachable. Okay, so if you close the RTP too quickly and the other side keeps sending RTP traffic, then you'll get some port unreachable, and that generates loads of traffic on the network, which is unnecessary. So we delay the RTP connection closing a little bit. And then on the other side, so if you need from the system, from the SBC to reach services outside, like NTP, like DHCP requests, like a ping from the system outside, this will go through the system automatically. So you have default settings. So normally you don't need to configure anything here, but you can change the default settings. So the default band duration, this is okay, default band duration. Yeah, it's 15 minutes, but you can change that. Okay, so then you can block for more or less time here if you get into the DDoS. And you see here the number of drop entries. The default is 2,000. So if you reach 2,000, sources that send you traffic and you don't want to receive traffic from those sources. And if you reach 2000, then we will fall into DDoS mode. Okay. And then you have also manual rules you can create in the system. So if you want to add rules, then you can configure them. And by default, it's going to use these parameters. For example, 400 packets per second for your manual rule. So it depends on what you want to use it for. If it's just to access the web portal, then you can keep this at a low value so that you don't block the traffic that is valid. Okay, and you make sure that you block invalid traffic here. Okay. But again, you don't need to create manual rules in the system unless you want to do something special. Okay, so access control rules are created automatically, like SIP trunks, like HTTPS, SNMP, SSH. You can add manual rules to accept or drop other type of traffic. The list is ordered, as you saw, and the rules are checked from the top down. As soon as the DDoS protection rule is reached and it is active, anything else will be dropped. Okay, so it's just like if you, instead of being the default drop down here, the default drop is now being pushed up here. Okay. Here you can change the order with these arrows here, but by default, you always have the dropping rule here at the bottom. So if it was not accepted in any one of those rules, it will be dropped here. You have automatic rules here that are created, HTTP, SSH, SNMP. And some of them, when you create a new network access point, it will open up some of those ports here to accept traffic. You can do some manual rules. So this was an example that we did. So this is to reach the system from an internal network. And you have here the DDoS special rule, so that when this kicks in, anything else below will not be accepted anymore. Okay, unless it was already accepted before. This is an example of a manual rule. So you can just go and create a special rule. And this is just an example. You say, I want to accept traffic from these IPs here, these IPs going to this IP. So you see 12358 is the web portal port. And then you have packets per second, bytes per second, so you can decide when you will block traffic going there. Well, actually, it's here, it's accept. So which traffic you will accept here. Okay. These are examples of packet matching filters, so you can create different rules like this. I don't want to go through this because it's fairly rare that we need to use manual rules, but you have some examples here. In the web portal, you can see the status of the firewall activity. So the SBC dropping packets or accepting packets, you can see them. You can search, so you have a box here that you can search for a source address, source port, destination address, destination port. Yeah, there's also protocols like protocol because it could be UDP, TCP, TLS, which port, which virtual port. And so you have all kinds of tricks here to find one packet that came in the system and may not have been accepted. Okay, so that's one way to debug a system, is that you think that you should have been receiving this particular request from this source IP to this port, or from this source IP and port to this destination IP and port. on this virtual port and da da da. So you can search for that and then figure out, why was it dropped, right? So you can see which rule it took and what's the state. And also how many packets you receive on this particular connection. All right, so you can look at this in the SBC status. So if you take just one of those entry, you can even get more details on here. Not only the source port and IP, you have also the type of VLAN. You also have when it was created. Okay, the type of rule. So you can get more details on that particular connection entry. You also get status of the SBC's firewall. You can see here DDoS alarm. So this is when it falls into DDoS, this will kick in here. You will see also how many times DDoS was kicked in. So you can see if you are continuously being under attack. If it was caused by a high CPU count, you will see it here. Normally, this I think should never happen. Or if it was caused by the drop entry list, which is full. Okay, and you see here the number of drop entries maximum and the current count of drop entries. So if you click on the second tab, you have rules. So you can see the rules that are created in the system. And for each of those rules, the filters. Right? So like I said, this is not used so much. And then, okay, this is another example. You see you have a virtual part, which is different. All punching means that it's coming from the system going out. All right, so that means it was accepted because there was a port that was open in the firewall for receiving a response. And then you can see here, if there's RTP traffic, it's going to be opened like this. And then if there's transcoding, you saw transcoding also goes through TB router. So then you see this here. And you see number of packet per second. And you see here, 50 packet per second peak, it's 50. So I know here this is G711 traffic going through this particular connection. Okay. And if I look on this here, I can see from which IP and port the traffic is being sent to and from. Okay. Yeah, just more example. Sometimes the status is not updated. Is there any service to refresh? You mean refresh what? The entries? Adam, do you mean the entries? The firewall entry status. Okay, this one here. So to refresh, yeah, here to refresh, you need to do apply every time. Yeah, unfortunately, there's no, because in some status pages, you have some refresh, right? So, Yeah, so sometimes you have refresh like this, but unfortunately they did not put it into this page. So you need to do apply every time to see it refreshed, right? If you do apply, does it refresh? Yeah, probably. So if your firewall is very busy, of course, this will be a busy rule like that, but you can maybe filter out a lot of traffic here to be able to focus more on what you need, right? And TB router status, I showed you already that you can go here in TB router and see the status of the applications. Not only, well, all the applications, but in particular TB router we're talking about here, and you can see the current state of the system. So if you look at this here, you will see how many packets per second, the bandwidth, the current bandwidth you're running on the system, and you see this update live. So this can be interesting to look at if you're not sure how much traffic you're getting through the system. Okay. All right, so that does the overview of the SBC details. Was there other questions on this part of the presentation? Okay. Yep. Can I change the management IP address after the initial installation? Yeah. So we do get this question a lot. So when you connect to the system and you have your management IP, you can see it here in IP interfaces, right? This one is using the HTTP and it's here. But as you can see, I cannot delete it here and I cannot modify it here. So if I click on this one, there's nothing I can do. Okay, so it's really used only for displaying the configuration. And for example, here I have a dynamic IP, DHCP, and I can see the IP that was allocated and also the gateway that was allocated for this particular interface. Okay, so I can only see it. If I want to change it, I need to go to that device. So that's webinar A4. So I just need to connect to webinar A4 SSH interface. Webinar A4. If I do my IF config -A, I will see my management 0 port, right? So the IP.242 and the net mask here that was allocated to this port, okay? If I want to change the management IP, I need to change it here, okay? There's two ways to do this. One is a tool that we have created that's called TB Change IP. So telco bridges change IP. And then it will ask you, do you want to modify the management interface? So you say, yes, I want to change management interface 0. And then right now it's set as DHCP, and you can modify this setting. So do you want to modify the settings? Yes. And now it's DHCP or static. So if you want to keep DHCP, fine, but you can change this to static. And then you need to enter your new IP address. Okay, so something like this. All right, you enter your net mask, you enter your gateway, and then you hit apply. When you hit apply, it will change the management IP of that system. Okay, and it asks you, do you want to restart the network service? If you restart the network service, you will be on the new IP, and you will probably have lost connection here because that's the connection you're using right now to connect to it. Okay, so that's one way to change it, by using the command tbchangeIP. The other one is by modifying the CentOS files, CentOS network files. Oops, I'm not in the right directory. Well, why don't I see my interfaces? Because I think it's because I'm in the HCP that I don't see it here. Yeah. But anyway, so that's, if you know how to use this, you can also change this interface manually like this. Okay. So, but definitely tbchangeIP is the recommended way because it has less chance of making a mistake in those files. The other thing I did not talk about about management interfaces is that it is possible to create a management interface on a LAN 1. All right, so you can just do a create new IP interface, but you will select it as either fixed management or OAMP. Okay, so if you select it as OAMP, so operation and management interface, then this management interface will follow the main OAM application. So if the OAM application is running on one server, you will, if you access this IP that you configure here, let me just do it, it's going to be easier. Like this here, and you choose a private IP. All right, so you can put an IP here. So if you put this IP, all right, 10.10.10.11, and you choose OAMP and NAT, this IP address will be on one system. And if the OAM master goes on the other system, then you will be on the other system. All right, so you will make sure that you're always following the master. But you can also set, instead of using OAMP, you can say fixed management. When doing this, you will need to choose which server you want to have this interface, and it will be locked up on that server. Okay. Did that answer your question of the management IP? Fabio, thank you. Okay, so Rudy said, in one portal host CPU usage, there is congestion. What does it mean? All right, so if I go back here in application, status, no, sorry, host and status, you have processor usage here. In this processor usage, you have percentage and congestion and maximum. Okay, so of course the absolute maximum means that if you reach 300, you won't be able to process new calls. Okay, you're completely busy, and it is not processing new calls. When you reach congestion, okay, we will change the behavior of the system so that the answers to the incoming legs will be different. Okay, so and I think the congestion here is the starting point, but if it reach from 240 to 300, the behavior will change. Okay, and as closer we get to the 300, we will start answering some of those messages. Okay, so initially we will start dropping some of those messages. I would say nicely, meaning that we will answer and say, okay, now we will drop this because we're too busy. But if it gets too high, too close to the maximum, then we'll stop dropping silently those messages. Okay, so there's different ways of managing that. So when we reach a congestion status, we'll modify the way we handle the traffic so that we don't overload the system. Yeah, and here I don't know why it doesn't show more than one threshold. Maybe we're missing a little bit of data here. But I know that between these two here, you will have more than one threshold reach. I think this is only for displaying the certain congestion level so that you know that you're getting close to the limit. But internally, it's going to be processed differently. Okay, and then we have for call trace, it stores in a file. Where is the location and what is the format? Okay, so the location of this file, I think it's shown here. Let me just, yeah. So it just says TBUCT writer. Okay, so that's not super useful. Oops. Okay, so the files look like this. They are called UCT data. UCT data. Okay, and they're stored in this path here. And this path here is reachable by TB setup. So you just type TB setup, and then you get to this folder, which is the application directory. And then in this case, we want to see the TBUCT writer files, which are call trace. And you will see all the UCT data files, which are calls that are being recorded on the system. So you see here, I was running probably a stress test here. You see there's a lot of files that were created on this date. And then when there's no traffic, then there's almost nothing being created in those files, okay? These files cannot be read straight like this. They need to be loaded up in the web interface here so that they can be seen in the call trace. And to do this, we have to go on the wiki. I think it's here. No, it is not here. It must be here. Retrieving call trace. Let me just look down here to see if I'm at the right place. Somewhere here. Yes, there you go. Okay. So this path, this link here, I'll put it in the chat. Retrieving calls from files. So by default, the system stores up to 10,000 call legs in memory. If there's no more memory left, then we also put them in a file. Okay, and this is the procedure to read that file. So it's a bit tricky, but once you've done it once, then you understand how that works. You start this tool. So again, the same tool that we're using usually. You select TBUCT writer. Then you need to use the option O to read the file. And then it's going to be displayed in the web interface. Okay, so you need to follow this procedure here to get those files. And then, okay, so one more thing is that when you load up the UCD data file, you will see them appear here in the call trace. So maybe you have loaded something from 2 days ago. So if it's 2 days ago, then of course you need to change the date here so that it reaches something that was done 2 days ago. Okay, and then you will see all the call traces here. But any new call will not be stored in this memory, okay? Because you don't want to overwrite what you're looking at right now. So you're studying a specific call trace, and you don't want to go over that. So to recover this, you need to press L option from the web portal. Okay, so let me just show you quickly here. If I go to call trace or TBUCT writer, okay, when you get into those menus here, you can always do help like this with the question mark. And you see here O to open the file, L to go back to live mode. So you have the instructions on how to do this here. So Rudy, does that help you? The next module is on TB analytics. So I will show you some stuff about it. Okay? So I suggest we take a break